Hi everyone, welcome back to Princeton and welcome to our PSSCMP summer school. Today we're very greatly honored to have Professor Fai Mak from Cornell University joining us and give us his second talk about magnetism in strongly correlated Moiré superlattices. Okay, Professor Mak, it's all yours now.
Okay, I will share my screen. You guys can hear me, no problem, right?
Yeah, we can hear you.
Okay, and screen. Arrow shown. Okay. Well, I want to thank Xiaoyu again for the introduction, and also I want to thank all the organizers for putting up this wonderful program together. I've been actually learning quite a bit from this workshop. And today, I'll just continue the theme on Moiré superlattices from yesterday's two lectures, beautiful lectures from Santhu. There is actually something quite different compared to yesterday's talk. Well, first of all, it's actually an experimental talk. And secondly, yesterday, Santhu has actually focused on graphene Moiré superlattices. And today, I will only tell you something about magnetism in two-dimensional semiconductor Moiré superlattices. And you will see actually that the physics turns out to be actually quite different. And the reason mainly is that the band topology in the system that I'm going to talk about is trivial. Okay, so in that sense, a lattice model that described by the Harbour model actually will work pretty well for the system. Okay, so a good starting point for our discussion would be the Harbour model. And well, solid state 101 model would be that, to describe the physics of quantum particles on a lattice is the tight binding model. In this model, you have a lattice and you have electrons described by one-year functions. And the electrons can actually hop between side to side and described by a hopping integral or hopping constant T. And the Hamiltonian is very simple. It's just has one term, which is the hopping of the electrons between sides. Okay, and the hopping will just turn the atomic levels of each atom in the lattice into a band, as we all know, and the bandwidth is proportional to the hopping constant T and the number of neighbors surrounding each atom. Well, in 1963, Harbour actually added an extra term to this Hamiltonian. In addition to the hopping, what he did is actually he added this term which describes the on-site Coulomb potential, the on-site Coulomb potential cause to add two electrons on the same lattice, and simply because the Coulomb repulsion between the electrons. So the Hamiltonian is actually modified to this form here. Now it has two terms. One is the hopping term again, and the other is that the on-site Coulomb U that describes the Coulomb repulsion. And there are only two terms in the Hamiltonian, and as a result, the physics is only controlled by the ratio of these two energy scales, U and the T. And we just call it U over T. And if U over T is very strong, and we call it strongly interacting, strongly correlated, when U over T is actually very small, then it's a weakly interacting system. Okay, and the Harbour model is very important. I don't need to emphasize it more. It's believed to be the correct model to describe a high temperature superconductivity, magnetism in insulators, and metal insulator transition, and a whole set of quantum phase transitions. So even with just this simple model. And let's see what the prediction is in some simple situations predicted by the Harbour model. And let's now consider a simple one-dimensional electron chain, or one-dimensional lattice like here. And we will consider a specific filling. We call it half filling of the band, or basically what it means is that you have one electron occupied each side. Okay, and so this is the configuration here. And of course, the electron can actually choose to hop between sides. For instance, the electron hop from the side I to side J here, and there are two electrons located at side J. We call it a doubleon. And by doing so, actually the electronic system can gain energy from the hopping on the order of T. Okay, but of course, if you actually include the on-site Coulomb U in the Hamiltonian, there's an energy penalty to do so, which is the on-site Coulomb U because of 2 electrons occupying side J now. And this is the prediction, a very schematic prediction of what will happen if you increase the ratio of the U over T at this a half filling. For small U over T, you will have a metallic system that is described by the Fermi liquid. But once you go over a critical U over T, and the Coulomb, the penalty is so large that actually an energy gap is opened in the system. And at very large U over T, this energy gap is basically the Coulomb energy cost to put 2 electrons on the same site. So the energy gap is around U in the system. And this is actually called a Mott transition. And the nature of this Mott transition is actually non-trivial in many cases. And not only that, the Harbour model can actually tell us things about the electrical conductivity in this model for materials described by this model. It also tells us something about magnetism, as also very briefly mentioned yesterday by Santil. Is that this is at the Hamiltonian again, and let's consider the situation that still at half filling, 1 electron per site, but we consider the limit that the U is much, much bigger than T, so that the T term can actually be described by the perturbation theory. So the system is very much in the insulating state, and we just turn on the hopping term as a perturbation. And without the hopping term, the system, the spins will be just, happily stay at each site and then independent of each other. But actually, this once you turn on the hopping term and you do a second order perturbation calculation, and what you will find out is that the system can actually gain energy on the order of negative T squared over U per particle by hopping, do a virtual hopping, say from side I to side J, to the next side, and then come back. Okay, and this is the energy gain. And in order to do so, spins of the 2 opposite sides, 2 adjacent sides actually have to be anti-aligned, so that effectively speaking, this tunneling process is corresponding to antiferromagnetic coupling in the ground state. And the ground state is an antiferromagnet with a super exchange energy scale that was first introduced by Phil Anderson on the order of T squared over U. Okay, so that's about the electrical conductivity behavior at half filling, and also the magnetism at half filling for the Harbour model in the large U over T limit. And what happened if you actually start doping electrons into the system? And it turns out that it's a very interesting problem. At the same time, it's extremely complicated. And let's get a little flavor of what will happen once you put an extra electron. Say, for example, by a gate voltage, you just put an extra electron onto the side I. And already the Coulomb energy cost U is already paid by doing so. And you already create a doublon in the system, 2 electrons occupying the site. And if the lattice is still remaining, the underlying electron background for half filling is still remained in the antiferromagnetic ground state, then in this one-dimensional chain case is that the electron just cannot hop within sites because of Pauli exclusion. But again, the system can actually gain energy by hopping, with the energy scale of T. But the antiferromagnetic exchange between, in one bond is only on the energy scale is only T squared over U. And in the large U over T limit, T squared over U is much, much smaller than T. So that the system actually, once you put 1 electron in, it can actually flip the spins of many bonds like this in order to gain the energy for hopping, right? So that this one hole can actually hop around, one electron can actually hop around in the background of a ferromagnetic ground state. So that what you would expect, this is a very schematic phase diagram, what you would expect for the magnetism for doping a Harbour model away from half filling or filling factor 1. Here is that at large U over the limit, you just need to add a little bit of doping and the system will turn into a ferromagnetic ground state. Okay. And in between, of course, things could become more complicated and the spins can be counted and things like that. But in general, is that it's a very rich phase diagram that would be predicted by just considering some basic physical principles for what will happen for a Mott insulator, and for a Harbour model. Okay, and so the situation is actually complicated, and it's nicely summarized by a Niche Physics editorial published in 2013. Is that the simplicity of the Harbour model when written down is actually deceptive, because it's actually very difficult to obtain the phase diagram of Harbour model. And in fact, only exact solution for the Harbour model only exists for the one-dimensional case obtained by Lieb and Wu in 1968, a few years after Harbour introduced the model. And in two-dimensional and three-dimensional systems, which actually are most relevant to most of the quantum materials, it turns out that actually this model is extremely difficult to solve it. And people over the years have developed lots of numerical methods. I listed a few here, but in general, it's still an unsolved question. Okay, so here comes the concept of quantum simulation, first introduced by Feynman in 1981 in a lecture. This is what Feynman said: let the computer itself. Well, the title of the talk is Simulating Physics with Computers, right? And what Feynman would like propose people to do is actually let the computer itself be built of quantum mechanical elements which obey quantum mechanical laws. Well, basically, this would mean that in the modern concept, it's a quantum computer. And but of course, Feynman did not tell us how to actually really build a quantum computer. But in the same lecture, he did propose something actually quite concrete, is the concept of a quantum simulator. This is the statement: there is to be an exact simulation that the computer will do exactly the same as nature. So what he meant is really that you have a Hamiltonian that you would actually like to simulate, and you find a physical system that exactly emulate this particular Hamiltonian you want to simulate. And by measuring this physical system you create in your lab, you obtain the solution or you obtain the phase diagram for this particular Hamiltonian. One famous example of quantum simulator is the AMO simulator based on trapped atoms and ions. Okay, and with this, then comes a Moiré superlattices, and it turns out that it's actually a very interesting new platform to try to simulate physics, because it's extremely controllable, the system, in terms of both the filling factor and may even be the interaction strength in the system that can be controlled very well by just apply a simple gate voltage. And so this actually, we believe that this is a game changer that stimulated by the study from Pablo in 2018. Okay, a few words on Moiré superlattices. I don't need to go too much into it because of yesterday's lecture. And Moiré superlattice actually can be formed by putting two materials together, even angle aligned, as long as they have different lattice constants. For instance, graphene and boron nitride, they have a lattice constant mismatch by about 1%. So you put them perfectly angle aligned on each other, you create Moiré superlattices shown in this figure here. Of course, you can also rotate it and you can change the Moiré superlattice period. But typically, we're interested in the regime that the superlattice period is on the order of 10 nanometer. And that's the Moiré wavelength, 10 nanometer. And you can also think of it, each Moiré site here is an artificial atom. And the atomic size is now significantly bigger. It's about 10 nanometer rather than an angstrom for real materials. And the extra periodic potential produced by this Moiré superlattice will just give extra Bragg reflections. And for instance, in this example here, the graphene simple Dirac-Cohn dispersion will be turned into something more complicated because of the zone folding effect. And the Brillouin zone is much smaller. Of course, you can also create a Moiré superlattice by twisting two homo bilayers on top of each other, right? The most famous example is graphene on graphene. If you angle align them, no Moiré superlattice can be formed, but as long as you rotate the angle a little bit, and you form a nice Moiré superlattice as shown here. And what's really triggering the field, the huge activity in the field, huge amount of activities in the field, is actually the prediction and the subsequent experimental realization that at around this magic angle, 1.1 degree, first predicted in 2010 and 2011, that very flat electronic bands can be formed near zero energy or near the Fermi energy there. And the speculation at the time is that once you have very flat energy bands, you actually can significantly enhance the interaction effect due to Coulomb interactions. And so there could be lots of interesting interaction physics going on, and maybe exotic phases of electronic matter. And people have to wait for 7 years before it's actually realized. In 2018, I don't need to highlight this study more. Pablo Herrero's group has realized a strong correlation physics into bilayer graphene near the magic angle and near the correlated insulating state on both sides. They have also observed superconductivity. Okay. So that's so much I want to talk about, graphene superlattices. I don't want to go too much more into it, but I want to actually point out one very practical problem with the twisted bilayer graphene research, is that the strong correlation physics only occurs very close to the magic angle, around 1.05 degree or 1.1 degree. And if you just move away from this magic angle a little bit, say plus minus 0.05 or plus minus 0.1 degree, it's a very small angle, and significant changes in the phase diagram can already happen. And in fact, if you, to be a little bit more quantitative, is that the U over T is maximum near this magic angle, and the U over T will actually quickly decay away from the strongly correlated limit once you go a little bit away from the angle. And why this is a practical problem, because when you make a sample, typically you have depending on the location on the sample, you have variation in the twist angle, and you can think of it as a twist angle disorder in the system. But if the strong correlation physics is so much dependent on the so sensitive on the twist angle, then you get lots of inhomogeneity happening in the sample. And that's why actually, in twisted bilayer graphene, even the same kind of devices from lab to lab, the properties can actually vary a lot from one device to another. And the reason that this strong correlation physics is so sensitive to the twist angle is because of the Dirac-Kong, or the zero energy gap nature in graphene. Okay. So can we actually build a Moiré superlattice structure that also exhibit very interesting correlation physics, but at the same time we can get rid of the magic angle problem. I call it the problem here. And so the right thing to look for is actually materials already with an energy gap, not like graphene with zero energy gap, but materials with an energy gap. So that maybe actually the strong correlation physics from this Moiré superlattices can be more robust. And this comes with our introduction into the monolayer transition metal dichocarbonized semiconductors, which was found to be a direct bandgap semiconductor in 2010. And this is the structure of a monolayer of this material. It has 3 layers of atoms, not like graphene. In the middle layer is actually occupied by transition metal ions, moly or tungsten, and top and the bottom are encapsulated by sulfur or selenium or tellurium, the chalcogen group in the periodic table. And from the top down view, it actually has a honeycomb lattice structure similar to graphene, but you can actually see that the A and the B sublattice sites are now occupied by 2 different kinds of atoms, not simply by carbon, so that the inversion symmetry in the crystal is already broken spontaneously. And this is the Brillouin zone of the system. And the most interesting things will actually only happen near the K and the K prime corners of the Brillouin zone. And this is a simplified band structure diagram of this material. It's a direct gap semiconductor. The broken sublattice symmetry will actually open up an energy gap at the K and the K prime point. And also because of the strong spin-off interaction, not like graphene, the moly and tungsten, this is 4D, this is 5D electrons, so that it actually has a very strong spin-off interaction, so that at each K and the K prime, there is a finite spin splitting due to the spin-orbit coupling. And the spin splitting is opposite sign from the K to the K prime because they are time reversal copies of each other. Okay, and for the pristine material, the Fermi energy is located in the middle of the gap, and we can actually use a gate voltage to tune the Fermi energy in the system continuously. All right, so let's see what happens if you put 2 different TMD semiconductors on top of each other. And for instance, the example would be tungsten selenide and tungsten sulfide bilayer. And let's, for simplicity, also consider the 0-degree alignment, perfectly aligned a sample in this case. And because of there is actually a 4% lattice mismatch between the tungsten sulfide and the tungsten selenide, a Moiré superlattice is automatically formed even at 0 degree. And also, I actually want to point out that you can verify yourself as long as you have a reasonably large lattice mismatch in the original host materials. The Moiré superlattice structure is actually less sensitive on angle misalignment disorder. You can actually change, vary the angle a little bit, say by 0.5 degree, has some kind of uncontrolled 0.5 degree alignment from one location to the other, but the Moiré superlattice structure will actually look more or less the same. So I would say that, in terms of this superlattice structure, it typically has a reduced disorder density compared to twisted homobilayers. Okay, of course, we have the superlattice potential from the Moiré superlattice that will introduce extra bright reflection. And as a result, it formed a Moiré minibands and a mini Brillouin zone. And this is the case for the layer of WSE2. And what happened for WS2? The bands are shifted. Actually, the semiconductor structure here, 2 different layers of semiconductor, they form something called a type 2 band alignment. What it means is actually that the conduction band is from one layer and the valence band orbital is actually from the other layer of the material. And you can also see that the conduction band of WSE2 and WS2, or the valence band between the two, are actually separated by a large energy scale, so that there's very little orbital mixing between the layers. And each of the bands in each of the layer is just experiencing a Moiré superlattice potential and produces these Moiré flat bands. Okay, comparison between the twisted bilayer graphene and TMD Moiré superlattices would actually be helpful. So there is in graphene, there is still the sublattice symmetry, right? So there's a 2-fold sublattice symmetry. The 2 layers are the same, so you have a 2-fold layer symmetry, and also you have time reversal symmetry in the system. So as a result, you actually have a total degeneracy of 8-fold. So it actually takes 8 electrons to fill the flat band in the graphene. But in the TMD heterobilayer, the sublattice symmetry in the host material is broken, so you don't have this 2-fold. And the layer symmetry is also broken, and only we have remained, the time reversal symmetry for the 2-fold spin. And the total degeneracy, or total degree of freedom of the electrons, is actually 2-fold. And as a result, the physics I can actually describe by a single band with electrons with 2-fold degrees of freedom in the system. So it has much reduced degrees of freedom. And actually, it's because of this fact that the topology, the band topology in this system is trivial compared to a graphene, that the band topology is actually non-trivial. In 2018, Wu and McDonald has predicted that actually, has proposed that this system, with just 2-fold electronic degree of freedom, can actually be mapped to a single band Harbour model. And as a result, it's actually a very interesting platform to explore the physics of the Harbour model on a triangular lattice. And you can basically think of it is that your Moiré superlattice as artificial atoms, and each of this atom is trapping electrons. Once you start doping electrons in the system, it's trapping the electrons at this particular site, for instance. And the electron can hop between sites with a hopping constant that's on the order of 5 to 10 milli-electron-volt for the first Moiré band, meaning for, sorry, let me just go back, meaning for this band or that band is about 5 to 10 milli-electron-volt. The on-site Coulomb repulsion you can estimate just using the 1/r or the Coulomb's law, that is E squared over the dielectric constant of the surrounding environment, and then the size of the 1-year orbital, which is about 2 nanometer, and you can actually estimate on-site Coulomb repulsion. The energy scale is on the order of 100 to 200 MeV. So it's really deeply into the strongly correlated regime that U is much, much bigger than the T in this type of material, and that's what we would expect. And you will see that in experiment, that's actually the case also. Okay, so the simple message here is that this system, if you realize it, it basically the physics is expected to be described by a simple Harbour model with electron hopping between sites and a large on-site Coulomb U. And I'll come back to some deviation from this prediction later in the talk. Okay, and a few more words on this Harbour model. It's on a triangular lattice. It's not on a square lattice like in the cuprates. So that actually at half filling, we expected to for square lattice we expected there to be antiferromagnetic ground state, but the triangular lattice is actually trickier because of the geometric frustration. And in general, there are lots of competing states with nearly the same energy in this kind of frustrated lattice system. So the phase diagram, we will also expect it to be very different compared to the square lattice case. For instance, let's just take a look at the half filling case, or filling factor equal to 1, or half filling of the band. For the square lattice case, actually, it has been, this is the phase diagram as a function of U over T in the system. It turns out that the ground state is always a Mott insulator. For a square lattice, it's always the antiferromagnetic Mott insulating ground state. But instead, for a triangular lattice, things could become a lot more complicated as you tune the U over T ratio in the system. At large U over T, the system is a Mott insulator, and then the ground state for the spins is actually a 120-degree neo-antiferromagnetic order, which is shown like this. For small U over T, it's actually a Fermi liquid. Okay, it's metallic phase and it's gapless. And near some critical values of U over T, it's called a non-magnetic insulator. And actually, people have speculated that this could be just a spin liquid in the system. So it's also, the system could actually provide a pretty interesting avenue if you can tune the U over T to explore the physics in this kind of phase diagram. Okay. Maybe it's a good point for me to answer some questions before I proceed to the experiment.
Okay, so thank you, Professor Mak. And for the first question from Chen Li, why is the type 2 alignment more insensitive in this order?
It's actually not really the type 2 alignment. It's more about the 4% lattice mismatch in the system. That because of the large lattice mismatch, you can actually calculate that the Moiré density is almost independent of angle for small twist angle. And you can actually put two sheets together and try to put some angle misalignment disorder in the system. And you'll find that it actually has less impact on the Moiré superlattice structure compared to a homobilayer system. It's not really related to the type 2, but it's more related to the lattice mismatch.
Okay, thank you. And the second question from Sofik, is there a way to understand why some regions trap more electrons?
Basically, in the limit that this band separation is large, you can think of it that the Moiré potential can actually be described by a harmonic potential form, which means it's a summation of sine and cosine periodic in space. And so you produce a potential minimum at some particular location, and it turns out that the location is around here. That location will just trap the electron at that particular site. You should think of it as like an artificial atom with a deeper potential at this artificial atom site.
Okay, thank you. I think we can save the rest of the question at the end.
Okay.
Thank you.
Let me just move on with our experiment. The first thing I want to tell you is about the Mott insulating state with a caveat on it, actually, and I'll comment on that. Okay. So first of all, how we make the Moiré, this TMD Moiré superlattices, we still use the same Scotch tape technique and Van der Waals transfer technique that exfoliate the constituent material and restack them into this particular sequence here. And this is the device structure. It has a tungsten sulfide on top of tungsten selenide, angle aligned. So because of lattice mismatch, again, it produces a Moiré superlattice structure like shown here. And it's encapsulated between hexagonal boron nitride, which is a very good insulator that serves as gate dielectric. And we put graphene top and the bottom gates around the device so that we can actually inject electrons or take out electrons, meaning that inject holes into this semiconductor heterostructure. In a sense, we just tune the Fermi energy using these gates here. And this is one of the typical device structure here. We put some extra electrodes around for transport measurement or capacitance measurement. And the Fermi energy can be tuned by the gates. And the convention here is actually that it requires 2 electrons per Moiré site to fully fill 1 Moiré miniband, meaning that if you strip your Fermi energy through 1 Moiré miniband here, you effectively put 2 electrons on one site. Okay. And how we actually make sure that we can actually angle align these 2 different materials, because it's actually not twisted bilayer graphene that you obtain. You have one piece of graphene, you tear it off, and then you restack them. And these are from 2 different exfoliations for the two different materials. In general, we don't know their crystal alignment. And we use a second harmonics generation and nonlinear optical technique. I don't want to go into the details, to actually help us to characterize the crystal alignment in each of these constituent crystals, and then we stack them on each other with an alignment uncertainty less than 1 degree usually, but it hardly matters in our case because the physics is actually quite insensitive to misalignment angle, as long as you don't do something crazy that go beyond 3 or 4 degree, something like that. As long as you keep it within 3 and 4 degree, the strong correlation physics will be there. And well, we will probe both the charge and the magnetic response in the system that I would just tell you. So first, this is a measurement of the 2-point resistance. I want to specify that this is a 2-point resistance rather than a 4-point resistance, so that you don't really take this measurement too quantitatively, but still it will tell you something very useful. So this is 2-point resistance as a function of hole doping density, meaning that we actually try to move our Fermi energy by the gates into the first Moiré band here. So that's hole doping density, or the filling factor of the Moiré superlattices. 2 here would mean that we fully fill the first valence band of the first Moiré valence band, and 1 here is half filling of the first Moiré valence band. Okay, and what you can immediately see here is that there are 2 resistance peaks show up at low temperature, one at filling factor equal to 1, one at filling factor equal to 2. Okay, and you can do some temperature dependence, and the filling factor equal to 1, sorry, this is half filling of the bands. The filling factor equal to 1 resistance will just grow very quickly with decreasing temperature, illustrating, it's it actually changes by orders of magnitude, illustrating its insulating character in the system. So the resistance peak at filling factor equal to 2, meaning full filling of a Moiré band here, can actually be understood based, in a simple single particle band insulator picture. That's because you just completely fill a Moiré band in the system. So there's an energy gap in the system that prevents electrical conduction. On the other hand, at half filling, if you don't consider any interaction effect, you would predict that the system would be a Fermi liquid and metallic-like state. There should not be a huge resistance peak that's shown here in the experiment, right? A filling factor equal to 1 or half filling of the band. But in the Harbour model, you will actually expect that in the large U over T limit, the large on-site Coulomb potential cause will just open up a charge gap in the system on the scale of U, so that it prevents electrical conduction, and the system will turn into a Mott insulator. And the size of the gap, we can actually get an estimate from the temperature dependence. The full filling, well, the filling factor 1 peak or half filling resistance peak managed at a temperature about 150 to 200 Kelvin. That will give us a very rough, I would want to point out that this is a very rough estimate of the energy scale of U that is on the order of 20 milli-electron volt in the system. And actually, if you remember what I mentioned before, that if you actually do a simple estimate based on the size of the one-year function in the system to calculate the energy scale U here, that you will conclude that it's about 100 to 200 MeV. So this energy scale obtained from experiment seems to be significantly smaller compared to what you would expect from theory. We have actually done more careful measurement of the gap size using compressibility measurements recently, and we still obtain the energy gap at full filling factor equal to 1 to be about 50 MeV. So it's still substantially smaller compared to the Coulomb U. And Liang Fu actually had an interesting idea that this may not be a simple Mott insulator in the system. Actually, it's actually like a charge transfer insulator, like in the cuprate superconductors. And if you're interested in, please go to this reference and read some of his proposals. And I would still say that experimental wise, we still don't know whether it's really a Mott insulator or a charge transfer insulator. So more studies are actually required to resolve this issue. Okay, how about the magnetic response? We actually expect that, antiferromagnetic behavior at half filling of the Moiré band, right, of filling factor equal to 1. Okay, so how do we probe the magnetic response of the system? And let me just give you a very quick reminder of what happens, what you would expect for localized spins. If these localized spins are non-interacting, they are independent of each other, and each of them under a finite magnetic field will just develop a Zeeman energy. It turns into two-level system. And because of thermal activation, you can actually calculate the magnetization in this system to be of this form here. And if you take a derivative of the magnetization with respect to magnetic field to obtain the spin susceptibility of the system, or the magnetic susceptibility, you actually will figure out that it has a Curie's form. It has a Curie's law, which is a constant divided by the temperature of the system, reflecting the fact that you have thermal activation of spins across this two-level system under a magnetic field. But now let's actually turn on the interaction between the spins, the exchange coupling J between neighboring spins. And in the mean field theory, that each of this localized spin will actually experience not only the external applied magnetic field, but also a molecular mean field from the surrounding spins in the system. And with this modification, this would be the total magnetic field that is sensed by each of the spin in the system. The magnetization can be written in this modified form. And if you calculate the spin susceptibility again, it turns into a Curie-Weiss law that instead of 1 over T, it's actually 1 over T minus theta. And theta is called the Curie-Weiss temperature, simply just the Weiss temperature. And the Weiss temperature is on the order of negative J. Basically, what it means is that it reflects the energy scale of the exchange interaction in this localized spin system. Okay, and if you can measure the spin susceptibility as a function of temperature, and if you obtain a theta that is bigger than 0, you can conclude that the system is ferromagnetic, and well, at least ferromagnetically interacting among the spins. And if theta is actually smaller than 0, it means it's actually antiferromagnetic in the system. But how do we measure the spin susceptibility in this material? Well, we typically have a sample area in this type of system of 1 micron square. It's a relatively small sample. Well, maybe this is a lower estimate of the size of the sample, but it's not much different compared to 1 micron square. And the Moiré period is 10 nanometer, roughly speaking. So you can think that, inside the whole sample, we roughly have 10,000 spins in the system, but it's sitting in an extremely large magnetic background from the substrate, right, and from other things in the system. So that it will, once you look at it, it seems the number of spins is actually very small, and it would be very hard to measure the magnetic susceptibility. And here comes actually the advantage of using optics to probe the physics of material systems, is that you can actually always choose a wavelength that is on resonance with a particular material you want to probe. In this case, we are actually interested in the first valence Moiré band physics here belong to the WSE2 layer. So we can actually pick a color that is on resonance with the exciton resonance in the WSE2 layer, so that all the response is actually exclusively coming from the WSE2 itself. We don't have a background problem by doing so. And the experiment is actually rather simple. What we do is actually that we shine broadband radiation into the material, and we record its reflection contrast spectrum. And that's what, for example, here shows a typical reflection contrast spectrum in this Moiré superlattice structure. There's a clear peak located at about 1.68 eV. That's the exciton peak, belong to the WSE2 layer that I talked about. And this is a specific filling factor equal to 1. Okay, and the data is taken at 0 magnetic field for both left-handed light and right-handed light. But you see actually no difference. The red line is exactly on top of the black line. Actually, you can hardly see the black line because the red line is exactly on top of it. So that the left and the right reflection contrast is exactly the same in a 0 Tesla limit. And as expected, because the system actually, we do not expect it to break time reversal symmetry at this temperature scale. But once you apply a magnetic field, and now you can immediately see a finite Zeeman splitting in the exciton peak for the left-handed light channel and the right-handed light channel. You see a finite Zeeman splitting. And I actually want to point out that this Zeeman splitting in the exciton is not only produced by the externally applied magnetic field, but it actually also has a mean field component that is produced by the surrounding spins nearby the excitons. You can think of it basically, I shine light onto the material, I produce the excitons here in the WSE2 layer, but it's surrounding by these localized spins, and the localized spins will produce a mean field on the exciton and has an extra Zeeman splitting from the mean field. But this is a more complete set of data that we slowly increase the magnetic field from 0 Tesla to 2 Tesla. We're still considering the filling factor equal to 1 case, or the half filling of the Moiré band in the Mott insulating state. We can extract the Zeeman energy as a function of magnetic field, like here, okay? And you can see that actually once you go, the magnetic field goes beyond 1 Tesla, the Zeeman splitting is actually quickly saturated. And the reason is that the magnetization of the nearby localized spin already saturated by the magnetic field at 1 Tesla. So this is actually an experimental evidence that the exciton is really seeing a mean field from the nearby localized spins. You can determine the slope, which is actually the G factor for the exciton, and you can do a little bit of math, and it's not difficult to actually figure out that the measurement of the G factor in this Zeeman splitting is actually proportional to the magnetic susceptibility of the localized spins in the system. So that this way, actually, we can have a pretty interesting way to measure the magnetic susceptibility of the localized spins in this particular system. Let's see how well it works. It works extremely well, actually. This is a magnetic susceptibility, or the G factor, as a function of temperature at half filling of the Moiré band, again, in the Mott insulating state. Or we can also plot that it's 1 over the susceptibility as a function of temperature in the system. And the black dots are data, and the red curve is the fit from Curie-Weiss law. And we can extract a Curie-Weiss temperature about -1 Kelvin from this measurement. And that would give us, about 50 to 100 microelectron volt exchange energy scale. And the important thing here is actually that the Curie-Weiss temperature is slightly negative. What it means is actually it's consistent with the antiferromagnetic exchange behavior that you would expect from the super exchange mechanism I talked at the beginning for half filling for full filling for filling factor equal to 1. Sorry, it's confusing between full filling factor equal to 1 and half filling of the Moiré band, but they are the same. Okay, we can furthermore actually estimate some energy scale into the system, but you should just take it as an order of magnitude estimate. Since we can actually estimate from the temperature dependence, U is on the order of 20 MeV, and the theta is about 100 micro EV, and we can actually estimate a U over T ratio about 20 in this system. So it's very strongly interacting, and in this large U over T limit, actually the system can be more or less described by a Heisenberg model on a triangular lattice. Well, we can also do, we can also try to measure at other filling factors in addition to the filling factor equal to 1. And this is the result at low temperature for the Zeeman splitting as a function of magnetic field determined from the exciton Zeeman splitting. And again, we can fit the slope near 0 magnetic field to extract the G factor, and as a result, the magnetic susceptibility. And we can do it as a function of temperature at all the different fillings. And here is the Curie-Weiss fit for the temperature-dependent magnetic susceptibility of the system at varying filling factors here. And you can actually see that for filling factor below 1 and the system. So this dashed line here is the perfect paramagnetic behavior that you would expect. And 1 over susceptibility here in this case is bigger than what you would expect for a paramagnetic system. That would only mean that the system is actually antiferromagnetic interacting. Okay, and here I just summarize, all the data obtained from this fit. On the right axis, it shows the Curie-Weiss temperature. It's actually the negative Curie-Weiss temperature as a function of the filling factor in the Moiré superlattice. And you can see that for filling factor less than 1.2, the system is actually antiferromagnetic, meaning it has a negative Curie-Weiss temperature. For filling factor larger than 1.2, it actually turns into slightly positive or near 0. So it's weakly ferromagnetic or paramagnetic for filling factor above 1.2. And at the same time, I also show the magnetic susceptibility at low temperature And you can actually see that the magnetic susceptibility tends to diverge near this 1.2 filling factor. So combining these two measurements, meaning that the vanishing Curie-wise temperature around a filling factor of 1.2 and the seemingly diverging magnetic susceptibility of the system at low temperature around this filling factor would suggest that there may be a quantum critical point around here, a magnetic quantum critical point around this filling factor here. And it would be very interesting to, for instance, use our technique that we developed, we discussed yesterday, for instance, to image the quantum critical fluctuations around this a 1.2 filling factor here. I can actually take 1 to 2 more questions before I proceed to.
Okay, thank you. So one of the questions from the anonymous attendee is the RCP signal at finite magnetic field seems to develop a side peak. Is there any understanding of its origin?
It's very, very good eyes. We don't have a clear understanding of why there is actually a side peak developed. One speculation would be that there could be, the excitons also is trapped by the Moiré potential. There could be more than one minimum in the Moiré potential for the excitons, right? It's different from the Moiré potential for the charge carrier. Is the Moiré potential for the excitons, meaning for the electron hole pair, could be just different compared to the charge carriers. And if it has 2 minimum, for instance, then we have 2 different species of the exciton. But it is unclear why there is a side peak at large magnetic field. But the side peak only shows up near large magnetic field.
Okay, thank you.
And it doesn't influence our analysis because we actually always focus on when we obtain the slope and just with a limit magnetic field of 0.2 Tesla. So it doesn't really affect the analysis.
Okay, and another question from Paolo is also here. So why does the exciton peak show an asymmetric fellowship if the system is an insulator?
Oh yeah, this is just purely a problem of optics. The reason is actually that the local electric field at the sample is actually dependent on the substrate nearby. You can see that it's a multi-layer structure, so the light has interference at this multi-layer structure, and the local electric field could be very different from the applied electric field from the instant electric field in the system. So that's a result of optical interference in this multi-thin film structure.
Okay, thank you. I think we can save the rest of the question to the end of the lecture.
Okay. So I will make a short digression now from magnetism in the system and show some unpublished results related to the charge order state in this system. And then I'll come back to talk about how these charge order states can be related to magnetism and why they're interesting for magnetism. And so far, we only have talked about the Harbour model with only the on-site U, Coulomb repulsion. But since the gate separation, the separation in the gate from the sample, I don't want to show the device structure again, is the physical separation between the gate and the sample is actually quite much bigger compared to the Moiré superlattice period here, so that we actually cannot ignore the long-range Coulomb potential between the electrons at different sites. For instance, here I show the inter-site Coulomb repulsion between this electron and that electron, right? So in general, we actually really have to include the long-range Coulomb potential in description of the physics in this system. And a more correct model to actually describe the physics in this system would be something called the extended Harbour model. It's extended in the sense that the H0 here is the original Harbour model Hamiltonian that takes account only the on-site Coulomb repulsion U, but we also have to add a term that is due to the long-range Coulomb potential between the interacting electrons. So we call it the different V's here, representing the Coulomb potential that is not the on-site U. And in fact, such effect has been seen in Feng Wang's group reported this year in Nature, that in addition to the Mott insulating state, there are some extra states, incompressible states that you can actually see in fractional filling factors. For instance, 1/3 filling of the Moiré superlattice, a 2/3 filling of the Moiré superlattice, and you see extra charge order states developed in these filling factors. And the reason here is that the Mott insulating state is trying to minimize the Coulomb onside U so that the electrons are nicely arranged in this periodic lattice, that 1 electron per Moiré site or per Moiré atom. But for this charge order state, what is really trying to minimize the system is the long-range Coulomb potential V. For these two specific states, actually what it's trying to minimize is to minimize the nearest neighbor Coulomb repulsion in the system. So it's organized in this a charge order state. And are there more such charge order states? And it turns out that in our new experiment enabled by a new technique that we developed recently, we actually have seen nearly 24 of this a charge order states in fractional filling factors. And let me just briefly tell you what this technique that we have developed and why it is actually useful in terms of probing the physics of the charge order states in this system. I call it the Rydberg state sensing technique, okay? And let's consider just a monolayer semiconductor, a monolayer TMD semiconductor. It is a WSE2, for instance. You shine light in, you create an electron hole pair in the system. It's called the excitons. It's really just a Coulomb bound electron hole pair. And by the way, the material is sitting in a dielectric constant specified by the epsilon, the dielectric constant epsilon. You can really think of this exciton as a hydrogen atom, really in a two-dimensional plane, okay, with a 1/r Coulomb potential that is attracting this electron hole pair. And because the exciton is actually living in this two-dimensional sheet, most of the field lines that's corresponding to the binding of this electron hole pair lives outside the plane, okay? So the exciton binding energy of this system is very sensitive to the dielectric constant that the material is sitting at. And you can actually simply write down the binding energy for the different excitonic states in this 2D hydrogen atom. And the details are not important. What I want you to actually focus on is that it's proportional to 1/epsilon squared. So the exciton binding energy is proportional to 1 over the dielectric constant square of the surrounding environment. And so now imagine if you put a two-dimensional electron gas, a 2DAC, nearby but not touching this two-dimensional semiconductor layer. And if this 2DAC is in the metallic state or compressible state, it will have a larger dielectric constant so that epsilon will increase and then the binding energy of the exciton will decrease. On the other hand, if this 2DAC is actually in the insulating state or incompressible state in the system, we would expect the epsilon or the dielectric constant of this 2DAC layer will be reduced. And as a result, the binding energy will be bigger. Okay. And let's see how it works for a very simple system. We just put a graphene very close to this monolayer semiconductor, but not directly touching it. We also, of course, still have the gates that we can tune the Fermi energy in the graphene. And this shows the 2s Rydberg state excitonic absorption spectrum. And this is the 1s state excitonic spectrum. This is the 2s state. And you can actually see very clear shifts of the 2s state energy, or effectively what it means is actually the exciton binding energy, because the exciton binding energy is basically the energy difference between here, the 1s state, and close to it, the 2s state is the exciton binding energy. And what you can see is actually that the exciton binding energy symmetrically decrease on both electron doping and hole doping of the graphene. The exciton binding energy is the maximum when the Fermi energy is located at a Dirac point, and that's expected because that's actually when the graphene is the most insulating case, when it's, the Fermi energy is at the Dirac point, so that the dielectric constant is the smallest, then you will have a larger exciton binding energy. But if you dope the graphene onto the hole side or the electron side, the dielectric constant of the graphene or the compressibility of the graphene will increase, and as a result, you decrease the exciton binding energy under the system. And actually, this shift here follows very nicely the density of states of the graphene. Well, you can also turn on the magnetic field in the graphene, and it develops Landau levels. And as your Fermi energy actually sweep through these Landau levels in the graphene, you can actually see systematic shift in the exciton binding energy, which is shown on the left here, which is really a shift in the energy of the 2s Rydberg state, as we just tune the Fermi energy through each of the Landau levels. And actually, the result compares extremely well with an independent compressibility measurement. You can actually see all the different Landau level indices that can be seen by this excitonic or Rydberg state sensing technique. Okay, so since it works so well, then we actually now can replace the graphene layer by something more interesting, at least to us, that we put a TMD Moiré layer and very close to this excitonic sensing layer here. And this TMD layer, of course, has a Moiré superlattice and it has a flat band physics, as we just have talked about. Okay, and I want to point out that why we actually want to use this technique to sense compressible or incompressible states in this system is because of the very large contact resistance to the TMD Moiré superlattice. So typically, it's extremely difficult to make metallic contacts to this system. So it's very difficult to perform a direct compressibility measurement in the system. So our technique works extremely well for very insulating samples. So here is the result showing that, again, the 2S Rydberg state optical absorption as a function of the gate voltage we apply to the system, or you can think of it as a function of the filling factor of the Moiré superlattice. And what I want to point out is actually that there are lots of states that we can see, is that I have already mentioned to you that the filling factor equal to -1 or -2 are the Mott insulating state and the band insulator, respectively. We can see these states on both the whole doping side, meaning that the Fermi energy is doping into the valence band, as well as on the electron side, that the Fermi energy is doping into the conduction band. So these are filling factor 1 and 2 are simply just the Mott insulating state and the band insulating state. But you can see that in addition to these states, we have seen a series of incompressible insulating states at fractional filling factors at both the filling factor smaller than 1, and also we can see a few more for filling factor above 1. We can perform a temperature dependence. Well, with increasing temperature, basically the incompressible states just systematically disappear one by one with increasing temperature. So, you can obtain the TC, the transition temperature of all these different charge order states, which is summarized in this table here, filling factor, transition temperature. And the bottom line, I don't want to go into the details because I'm running out of time, is that these different charge order states can be very well described by a model, by a classical model, which only takes into account the long-range Coulomb interaction between electrons. And this, I just draw down the different charge order states that we actually have observed in this various fractional filling states here. Okay, and I don't want to go too much into detail. Then the last minute, I just want to actually tell you why actually we talk about these charge order states and why they are potentially interesting for magnetism. So this is the set of charge order states we actually have observed in our system. And you can think of it basically, it's an electron lattice in the system, but it's an electron lattice that can be changed by just a simple gate voltage. So you can think of it, it's a programmable electron or a spin lattice in the system. And once you turn on the interside hopping between the electrons in this system, you are turning on the magnetic exchange interaction. So it's actually a very interesting system to simulate, spin models with different lattices. For instance, we can actually simulate the Heisenberg model on a quasi-1D spin chain at the filling factor equal to 1/2. We can simulate the Heisenberg model, for two-dimensional Heisenberg model on non-frustrated honeycomb lattice like the filling factor 1/3 and 2/3. Okay. We can also simulate, a filling factor equal to 1. We already talked about, it's a simulation of the Heisenberg model on a triangular lattice. So it's really quite a programmable spin simulator on one single system that once you change the gate voltage, you can change the lattice symmetry of the underlying spin model. And it's very interesting to explore in the future. And I think I am basically close to running out of time, but let me just quickly tell you that this is a more carefully measured Curie-wise temperature using the technique that I told you about, exciton sensing technique. And as a function of the filling factor, 1 here is the Mott insulating state we already talked about. At this 2/3 filling with a charge order state with a honeycomb lattice structure, we can actually see a sharply enhanced Curie-wise temperature around this particular filling factor corresponding to a discharge order state. And we can actually understand the physics reasonably well, that why there is a enhanced antiferromagnetic exchange in this system near this is a two-third filling, and I don't think I have enough time to go through that. It's just some kind of an interesting itinerant whole exchange process, but I will skip that. So just to summarize, I hope I have convinced you that actually this is a very interesting system to, a very controllable and interesting system to simulate the Harbour model and various spin models on different lattice symmetries. And there are many remaining questions that actually need to be addressed in this system, and lots of interesting things to be discovered. For instance, whether we can observe superconductivity in the system. And we also have observed the stripe phases. I didn't have time to go through, and whether superconductivity is actually related to the stripe phases in this system is an interesting question. And the existence of the itinerant magnetism at the compressible region is also interesting. And we can also explore whether we can continuously tune the interaction strength in the system, and etc. Okay, so there are many open questions, interesting open questions remain to be explored in this system. And with this, I just acknowledge people in this work, our postdoc, Yanhao Tang, who's responsible for the first experiment, and graduate student Li Zhongli and Tingxin Li, a postdoc in our group. And Yang Shu is responsible for the exciton sensing experiment, and Chen Haojin and Zui Ta are responsible, and Tingxin Li also responsible for the stripe phases work, which I did not have the time to talk about. And we have a joint group with Professor Ji Shan at Cornell University. And we also acknowledge the theory support from Professor Alan McDonald from UT Austin and Veit Alser at Cornell University. And TMD crystals, very nice TMD crystal from Jim Hong's group at Columbia, and also a boron nitride crystal from the Japanese group. And with this, I thank you for your attention. And happy to take any questions.
Okay, thank you, Professor Max. Thanks for the talk. And so we have 22 questions. So for the first 5 questions, if I remember correctly, that should go back to the part before the experiment. The first question from Pavel: how extensively can one modulate U with a dielectric substrate? For example, like strontium titanium oxide.
Yeah, that's a very interesting question. You can do a simple estimate, and actually the U is very well, let me just show here. The U is very well, quite well estimated by this form here. And I would say that we know quite well the one-year orbital function. The size of the one-year orbital in this system is about 2 nanometer. And you can just plug in and calculate. And for strontium titanate, for instance, the low temperature dielectric constants can vary by orders of magnitude. And this U can be actually effectively modulated. And that's a very interesting proposal to tune the U in the system. Yeah, it's really interesting. You can actually map out this phase diagram, for instance.
Thank you. And the next question from Nitish: how can we change U over T in real materials?
In real materials, meaning, for instance, like in oxides or like that, it will be extremely hard, to change a U over T, right? Because the U over T in those materials is given by God, basically, or given by the periodic table. And but in this Moiré system, is actually there's a way to tune the interaction strength. So I would say that the Moiré system is somewhat like the AMO system in this sense, that there is a the level of control is much more compared to conventional material. And I think this is the most attractive aspect of the Moiré system. And we just have discussed, how one could potentially tune the U by dielectric screening, right? Okay,
thank you. And the next question from Yiping: does this TMD Moiré require similar lattice constant?
It doesn't actually. So for instance, here it has a 4% lattice mismatch. It's not a super huge lattice mismatch, but it's also substantial. 4% is quite a substantial lattice mismatch. So you don't need to find materials that with lattice matched. Of course, you can also form Moiré superlattice structure in a homobilayer system like WSE2 on WSE2. Then you would just do a twist angle similar to the situation in graphene.
Okay, thank you. And the next question from Jenna Xiang, sorry if I didn't pronounce your name correctly. So what is the role of the p orbitals from selenium and telluride in the superconductivity in this system?
So the first of all, nobody actually has observed a superconductivity in this system. It will be very interesting to observe, superconductivity in this strongly correlated system. But the p orbital, even we observe superconductivity, the p orbital would be actually not really relevant. The p orbital from the chalcogen atoms, because they actually form a large energy scale bonding and anti-bonding states. So they are very far away from the Fermi energy. They are just the remote bands.
Okay, thank you. And the next question from Chen Li. How can one experimentally turn twin U over T to access the spin liquid phase?
I guess we have just discussed that. One potential is just to tune the epsilon here, right? It's yeah.
Okay, and thank you. And the next question from Pavel. How large are the gaps between the flat band and the next bands in tungsten diselenide and over tungsten disulfide? Does their presence significantly affect the physics?
Yeah, actually, that's a very interesting question. And actually, that's a question related to how valid the Mott insulator picture is. So the separation between the Moiré bands is, the energy gap here is on the order of 20 to 30 milli-electron volt. Okay, so that's roughly the strength of the Moiré potential in the system. It's about 20 to 30 milli-electron volt in the system. And it's substantially smaller than the Coulomb U that you would estimate from the simple electrostatics formula here. And so that would actually cast questions on how valid, because the Coulomb U would actually tend to mix these different orbitals. I would say that for filling factor less than half filling of this system, you can pretty much think of it as a single band Harbour model. But for filling factor larger than half filling, the physics is actually becoming extremely more complicated because simply because the Coulomb U is actually much bigger than the Moiré band separation. And indeed, you can actually see that from very nicely see that in the charge order state physics here, is that for filling factor less than 1, you see a series of charge order state, but for filling factor bigger than 1, you don't actually see that many. And that actually reflects that the significantly reduced Coulomb interaction strength for filling factor bigger than 1. And I think that's actually related to the band mixing from the large on-site U compared to the energy scale of the Moiré band separation.
Okay, thank you. And the next question from an anonymous attendee. So it's a technical questions. Do you use graphite as contact? Is there any advantage over, for example, platinum? Why not use 4-point probe?
Yeah, graphene is not a good contact to this material. Actually, platinum is much better contact in terms of the whole doping side of the system because of the large work function of the platinum. And indeed, you can actually form quite reasonable contact to the whole side of this material with some twist, some improvements in the contacts, how to make contacts to this material. But you still have a very large resistance, contact resistance, even you improve the contact, especially for the whole low doping density below half filling the set. We tried, it's just very hard to make electrical contacts that can perform nice 4-point measurement or reliable 4-point measurements below this filling factor equal to 1. But it doesn't mean that it doesn't work. It's just probably some other people have to make it work. Yeah.
Okay, thank you. And the next question is also from an anonymous attendee. So why is full filling more resistive than half filling?
We actually have performed a full filling. No, meaning that this filling factor 1 is a resistance larger than this, right? I guess that's the question. And we actually have used a compressibility measurement to measure the gap size of the system. Or you can actually take a look at the temperature dependence here for the different charge order states. And you can see that actually the filling factor equal to 1 state, it has a much higher energy scale compared to filling factor equal to 2 states. And it's, the larger resistance is a result of the larger gap, actually, the larger Coulomb gap in the system compared to this gap at the filling factor equal to 2.
Okay, thank you. And the next two questions are from Christian. The first question is, Why do we see a plateau of the magnetic susceptibility near filling factor 1.2?
Why do I see excitons? Maybe I can show the data in here. This actually shows the excitonic resonance. So this is the excitonic resonance. Oh, this is the excitonic resonance of the WSE2 layer at varying filling factor. So this is filling factor equal to 1. This is filling factor equal to 2. So over a large range of the filling factor, also for the electron side as well, we can actually see a very clear excitonic resonance in the system. I think simply because the size of the excitons in this system, the excitons are very tightly bound. The wave function or the ball radius of the exciton is only 2 nanometer. So that it's actually much smaller compared to the Moiré wavelengths. So the excitons are actually very robust in this system. So that's why we can actually still see the excitons at varying filling factors.
Okay, the second question is, how does the Mermin-Wagner theorem play into this ordering?
Yeah, so what we are measuring here is it's an extracted Curie-Weiss temperature from a Curie-Weiss fit, which is essentially a mean field theory, right? That's only valid in the high temperature limit or the high energy scale limit. And once you cool down to lower temperature, you have different factors that may prevent the system from ordering. For instance, at filling factor exactly equal to 1, you have geometric frustration from the triangular lattice structure. And also at the same time, the system is 2-dimensional. And as a result, it's basically also effectively a Heisenberg spin system. We call it actually a Heisenberg pseudo-spin system. So that we would expect no long-range order, if we completely trust the Mermin-Wagner theorem for this Heisenberg model at 2 dimension. So I don't expect we actually see magnetic ordering, at finite temperature.
Thank you. And the next question is from an anonymous attendee. How one can distinguish that the magnetic response is coming from Moiré superlattice or some other defects in the system, which is common in TMDs?
Defects. So these TMD crystals are actually very, very clean. The defect density is on the order of 10 to the 11 per centimeter square. And the Moiré density is, the Moiré density is 2 times 10 to the 12. So it's substantially larger than the defect density in the system. So what that means is actually that we have, on average, 1 defect over probably 10 to 20 Moiré sites. So in terms of natural defect in the system, we don't think it's very significant. But of course, you still have the defects, or disorder in the Moiré superlattice structure, and how that impacts the magnetic response. That would be an interesting question. What I mean? I mean, a Moiré superlattice disorder rather than the original defects in the material itself. I believe that the defect in the material itself is not very important.
Thank you. And the next question from Shiming. Is it magnetic ordered or not ordered? Why the critical, I think. So why the critical filling factor is at 1.2 rather than 1.0?
So 1.0 is the Mott insulating state, right? Or actually it could be slightly more complicated. It could be a charge order insulating state, a charge transfer insulating state. But irrespective of whether it's a charge or a transfer insulator or a Mott insulator, you would expect antiferromagnetic exchange at a filling factor equal to 1.0 because of the super exchange mechanism proposed by Phil Anderson. So this this is actually in complete agreement with the theoretical expectation that this is slightly antiferromagnetic. Why this is actually happening here, I don't think I have a very good answer to you. Why there's a crossover or a transition around 1.2 filling factor. I don't think I can give a microscopic mechanism for this change.
Okay, thank you.
It's a complicated problem once you dope electrons or holes into away from half filling.
Okay. And the next question from Katra. Does the arrows in the mode insulator represent actual spin or an effective pseudo spin?
It's actually a good question. It's effective pseudospin, because the spin is already, because of spin orbit interaction, the spins in this system is already locked to the direction of the spin orbit field, which is actually out of plane in this material. So the real spin is really like effective Ising spins, but the model itself is actually is mapped into a pseudospin Harbour model. You can think of it. It's actually the value pseudospin in the system, K and K prime. That's a good question.
Thank you. And the next question from Sumit. Why is there a dip in the LCP signal?
A dip. Yeah, I think we have discussed a little on that. This is due to the optical interference in this multi-thin film structure.
Okay, thank you. And the next question from Shiming raised his hand, so let's bring him to talk. Okay, wait for a minute. Okay, now Shiming, you're allowed to talk.
So sorry, I clicked the wrong button. I need to click the Q&A. No, not this one. Yeah.
Okay. Okay, please type in your question in the Q&A. Okay, and so the next question from an anonymous attendee. So you have mentioned that the Zeeman splitting observes coming from both the magnetic field applied and the molecular field. However, when there is no applied field from both signals, right and left polarized are the same. Is there a magnetic finite transition when you turn the magnetic field? If not, why can you consider the Zeeman splitting as a signal of both effects?
Yeah, so first of all, we don't see anything, any difference between left and right at zero magnetic field, because there's no evidence in our system that it's ferromagnetically ordered. So if it's a ferromagnetically ordered in this system, spontaneously ferromagnetic ordered, we would actually expect to see a spontaneous difference in the left and right absorption at zero magnetic field. And why we would actually think that there is really a contribution coming from this molecular field from the localized spins is that Zeeman splitting quickly saturates at 1 Tesla. For instance, you can do the same measurement on a bare WSE2 monolayer. And in that case, actually the Zeeman splitting, first of all, is extremely small. And secondly, it's just linear up to, people have measured up to 60 Tesla. There is still a linear Zeeman, Zeeman splitting in the system. So this nonlinearity is really, the saturation of this Zeeman splitting is really reflecting that the underlying magnetization of the Moiré superlattice is actually saturated by the applied magnetic field. And that's why we think that it is related to the mean field, the molecular field from the localized spins.
Okay, thank you. And I think due to the limit of time, we will take the last question about the last part of the talk. So it's from Yihan. What's the system where you observe the fractional incompressible state using Rydberg sensing? How did you assess positive filling?
So this is the same system that we talk about. Is a WSE2 on WS2. So this system is just the same Moiré system we talk about. There's no change in the material system. What's the second part of the question?
So how did you access the positive filling?
Oh, the positive, we have a gate, right? So yeah, so we have electrodes that's touching this material. Well, I think the question is because I made a comment on that it's actually pretty difficult to perform electrical measurements on this material because of the back context of this material, right? And so performing electrical measurement is, you need very good context, but in terms of putting charge into the system, you actually do not need very good contact. Even actually for very bad contact, you can still put charge into the system as long as you wait long enough. And the context to this system is not that bad that actually we can still put a charge into the system. I mean, it's bad enough that we cannot perform reliable 4-point resistance measurement, but it's actually totally fine in terms of just injecting charge into the system. In terms of charging of the system, it's completely fine.
Okay, thank you. And sorry for the rest of attendees who have asked questions. We still have 16 questions left, but we don't have enough time to answer all of the questions. So please email Professor Mak directly if you have more questions and for further discussion. And
Okay.
thanks, Professor Mark, for the talk and for joining our
Thank you
summer
for
school.
hosting. Yeah.